this episode, we will be learning about electron configuration. So last time, when we talked about atoms, we talked about how electrons were just in the space outside the nucleus. Today, we're going to be looking more specifically at exactly where outside the nucleus electrons are found, or maybe inexactly where. You may have learned before that light exists as waves, um, and we have what's called the electromagnetic spectrum that you need to make sure that you know. It goes anywhere from radio waves to gamma rays. Radio waves is the low frequency, long wavelength, low energy side of the spectrum. Gamma rays are the high frequency, short wavelength, and low energy side of the spectrum. You want to make sure you understand some things about light. The speed of light is 3 times 10 to the 8th meters per second. It's the fastest speed anything can go in the universe. The speed of light is related to frequency and wavelength. Here F is frequency and W is wavelength and C is the speed of light. If you multiply those two together, it's always the same constant. Early on in the 20th century, physicists realized there were some problems with the wave model of light. One of those problems was that whenever an object has a certain temperature, it always has a certain characteristic spectrum called the black body spectrum associated with it. Physicists couldn't find any way of using the wave model of light to fit this spectrum. So they had to turn, and then the other problem there was looking at how different elements absorb different characteristic colors of light or emit different characteristic colors of light when they are excited. So we can see off on the side here these different kind of rainbow colors. The top one shows an absorption spectrum where only certain colors of light have been absorbed, and the other ones show emission spectrums. Okay, so physicists couldn't answer why black body radiation worked the way it did with classical physical mechanics, and they also couldn't work out these absorptions and emission spectrums. So this created a problem that had to be solved. Planck had, which is a scientist, Maxwell Planck, I think Maxwell, had an idea that energy maybe can only come in certain size packets. And so this is the quantization of energy. And he came up with this famous expression that the amount of energy that one of these quantum of energy has is related to this constant h, which is referred to as Planck's constant, times the frequency, which a lot of times frequency is kind of written in this script V, although my program could only make a normal V, but usually it's kind of a curvy V. Okay, so the idea is that before Planck came around, people thought that energy could exist in any amount. So if I wanted to take this ball up a hill, the ball could rest anywhere. It could be at the bottom of the hill, and it could be at the top of the hill, or anywhere in between, as long as it's sitting on the slope. What Planck realized is that maybe energy couldn't exist in any value, that it could only exist in certain values. So the ball could be at the top or the bottom of the hill, the ball could be up at the top of the hill, or the ball could exist on different steps, but it could not exist anywhere in between. So for example, the ball can't be halfway between these two steps. It has to be on one step or another step. To Planck, this explained some issues along with black body radiation and also some issues with these absorption and emission spectrums. And we'll get into how that works in a moment. One thing that supported Planck's idea of this quantization of energy was an experiment called the photoelectric effect. And this was described in a paper by Einstein in the early 1900s. If I shine light on a piece of metal, okay, so I'm going to start off with a red light here. Well, now I'll start with the purple. So if I shine even a low intensity purple light on a piece of metal, as the light hits the metal, it causes electrons to be kicked loose, and that induces a current in a circuit that's made between them. And this happens even for a low intensity purple light. If I shine a red light on the piece of metal, the current drops to nothing. Even if I take the intensity way up and make it a super bright light, still nothing happens. What Einstein realized is that this shows that energy is quantized. The purple light having a short wavelength, each packet of light coming in and hitting the metal has enough energy to kick the electrons off of the metal. However, red light having a longer wavelength and thus less energy, each packet of energy that hits the metal is not enough to kick an electron off and therefore cannot cause the current in the circuit. So we have different competing models of how an atom should behave. So the first model, just thinking of atoms as billiard balls, if you shine a light on a billiard ball, these little packets of light energy, like any of them that hit the billiard ball, should bounce off. And so you'd get a spectrum of absorption where the atom was able to absorb any color of light. If you think about a plum pudding model of this, any color of light that hits the atom would cause the charges inside the plum pudding to be excited and wobble. And again, we would have a spectrum that reflected that. If we had a solar system model where the electron had to be in a certain place, it just wouldn't work at all. Now Bohr came along with the model, and he's with this whole quantumization idea, and you can see that when the electron gets hit by different colors of light, it is caused to jump from one orbit to another, and that was the way Bohr described how we should get these absorptions. So only certain colors can cause the correct jump from level to level. De Broglie complicated more. He wanted to look like, well, why does the electron only fit in certain places? And so he thought of electrons as waves. And so these waves could fit in certain places around the nucleus and not others. And so when the electrons got hit by light, they would be excited, and the frequency of the wave would change. The amount of energy the wave had would change, and so the wave would fit in a different place around the atom. Then with Schrodinger, he realized that still that locks the electron into a certain place, and that's, we can't actually narrow down where electrons are. And so electrons just have areas of where they probably are, and then when they get excited, depending on how much energy you have, the model of where to look for electrons changes. And so this Schrodinger model of the atom, of electrons not having certain orbits, but just areas of where they're likely to be found, is now the current model of the atom, and we'll be working with this one in class. So what we need to take away from this is matter, like light, is both a particle and a wave. So light is a wave, and each wavelength has its characteristic color and everything else, but it's also a particle, and each particle carries a certain amount of energy. Matter is like that also. We also need to learn about Heisenberg's uncertainty principle, which is telling us that we can't know exactly where and how fast an electron is moving at the same time. And that's why we get this Schrodinger model of we only know where the electrons probably are, not exactly where they are. These ideas lead to electrons not occupying orbits like planets going around the sun, but rather that they are in orbitals, which are just regions where they are likely to be found. So each electron can be described by different quantum numbers, and it has to have its own unique set of quantum numbers for that atom. The 4 different quantum numbers are n, l, m sub l, and m sub s. N is the principal energy level, and it can be anywhere from 1, 2, 3, any integer up to infinity, although for real atoms they never get that high. L designates a sublevel, so within each level there are sublevels, and the sublevels can run anywhere from what the principal, anywhere to up to one less of the principal level, so they can be 0, 1, 2, and so on. M sub L designates a specific orbital range, and M sub S designates an electron spin, which is either up or down. So here's a convenient table that talks about the principal energy level, what sublevel can be contained, and then what orbitals are present. So in principal energy level 1, you can only just have one sublevel, the 1s, which only has one orbital, the 1s. Principal energy level 2 has two sublevels, the 2s and the 2p, and a 2p sublevel has three types, the 2px, the 2py, and the 2pz. And you can see every time an energy level is added, another sublevel is also added. So the third energy level has three sublevels, and the fourth has four. The D's have 5 types, the F's have 7 types. If we were looking at G's, G's would have 9 types, and so on and so on. Okay, each orbital can hold 2 electrons. So in the first energy level, you have one orbital, you can hold 2 electrons. In the second energy level, you can hold 2, 4, 6, 8 electrons. In the next level, you can hold 18, and so on and so on. Here are some pictures of what these orbitals, the shapes of these areas of probability look like. You can see for the S, the P, and then so the PX, the PY, and the PZ, each one goes in a different direction of space. One skill you'll be learning how to do is how to fill up energy level diagrams. So here's what an energy level diagram shows, how the energy of an orbital changes as you go through the different levels. If you want to know what the electron configuration is for an atom, what you need to do is fill this up with given a certain number of electrons. And I'm going to go specifically into this in a second video since we're kind of running low on time.